Hello friends, I welcome you in lecture number 22 on relations. In this lecture also we are going to discuss one more example on composition of relations. So let's start with this example. Here we are given some relations on this set of real numbers. That is, we are given the subsets of R cross R, which we denote by R2 also. So instead of writing R cross R, we can use this notation R2, and we are given the relations on the set of real numbers. That is, all these relations are subsets of R2 or R cross R. R1 is defined as set of all those ordered pairs AB in R2 for which A is greater than B. That is, first component is strictly greater than second component. Similarly, all other relations are defined using some condition on the components. R4 is defined as all those ordered pairs AB for which A is less than or equal to B. Here in R5 condition is A and B are equal, here A and B are different. So we have to decide all these compositions for these relations on the set of real numbers. So we start with part A. Here we should find out composition of R1 and R2. So let me write R1 first. In R1 condition is A greater than B, and in R2 condition is A greater than or equal to B. R1 is the set of all those ordered pairs for which A is greater than B, and R2 is the set of all those ordered pairs AB in R2 for which A is greater than or equal to B. And I have to find out R1 composite R2. That is, I have to decide the elements order pair AC in R1 composite R2. So I have to decide that which condition I have to put on this A and C such that order pair AC belongs to R1 composite R2. So we know that ordered pair AC is in the composition of R1 and R2 if there exists some real number B such that AB is in R1 and BC is in R2. If this happens for some real number B, then we can say that this order pair AC is a member of composition of R1 and R2. This is by definition. By definition of composition, ordered pair AC belongs to R1 composite R2 if AB belongs to R1 and BC belongs to R2 for some B belongs to R. Now AB belongs to R1 if this ordered pair AB satisfies the condition of this relation R1. Here condition is that first component must be strictly greater than second component. So AB belongs to R1 implies A greater than B, and BC is in R2. In R2 condition is that first component is greater than or equal to second component. Here I have written ordered pair AB. Ordered pair AB is in R2 if A is greater than or equal to B. Therefore, ordered pair BC is in R2 if B is greater than or equal to C. Now we require condition on this A and C. So here we can see A is greater than B and B is greater than or equal to C. We can combine these two and we can write that from this A is greater than B, B is greater than or equal to C, and from this I can write that A is strictly greater than C. Therefore, I obtain the condition on this ordered pair AC to be an element of R1 composite R2. Therefore, this relation R1 composite R2 is the set of all those ordered pairs AC in R2 which satisfy this condition, A is greater than C. Now here A and C are arbitrary, so we can replace C by some other number, say B also. So we obtain this condition, A is greater than B, or we can keep this as it is. But I have replaced C by B because it is arbitrary, so I can write any other number for instead of C also. And this I have written to explain that this relation is nothing but relation R1. In relation R1 we have those ordered pairs AB for which first component is strictly greater than second component. So here also you can see, if I am writing AC, then also it is obvious that this relation is the set of all those ordered pairs for which first component is strictly greater than second component. So this is nothing but relation R1. So what we have obtained, composition of R1 and R2 is nothing but R1. So this is first part. Now we go to the second part. We are simply using the definition of composition of relation. Second relation is R2 composite R2, composition of R2 with itself. And we have written what is R2. R2 is the set of all those ordered pairs AB for which this condition is satisfied. Here equality is also allowed. So we have to decide that which type of elements are in R2 composite R2. So we start by the definition. Again we consider arbitrary element in R2 composite R2. AC belongs to R2 composite R2 if there exists some real number B such that AB belongs to R2. First relation is R2 and BC belongs to R2. Here second relation is also R2, and this is for some real number B or for some B in the set of real numbers. Now from this we try to find out condition on these elements of this ordered pair. Now AB belongs to R2 implies A is greater than or equal to B, and BC is also in R2. In R2 condition is first component can be greater than or equal to second component. Here first component is B, second component is C. And if we combine these two, therefore we can write that A is greater than or equal to B and B is greater than or equal to C. And using this I can write that A can be greater than or equal to C. If B and C are equal, then we can write that A is greater than or equal to C, or we can write A is strictly greater than C if B is strictly greater than C. So in short, we obtain the condition on A and C to be an element of R2 composite R2, and condition is that first component is greater than or equal to C. So what we have obtained for R2 composite R2, this is equal to all those ordered pairs AC in R2 for which A is greater than or equal to C. And this is nothing but relation R2 itself. In relation R2, condition is that first component can be greater than or equal to second component. So R2 composite R2 turns out to be R2 itself. So this is part B. Third part is R5 composite R3. So let's find out R5 composite R3. For that, let me write R5 again. R5 is the set of all those ordered pairs AB in R2 such that A equal to B, and R3 is the set of all those ordered pairs in R2 such that, let me check what is R3 and R5 again. For R3 condition is A less than B, for R5 it is equality. So let me write R3 here. R3 is less than relation, A is less than B. Now again we start by considering arbitrary element in the composition of R5 and R3. AC belongs to R5 composite R3 if for some element B we have AB belongs to first relation, that is R5, and BC belongs to second relation, that is R3, and this is for some B belongs to R. This is by definition. AB belongs to R5 gives me that A and B are equal, and BC belongs to R3. In R3 condition is that A is less than B, that is first component is less than second component. Now here A and B are equal and B is less than C. So if I put B equal to A here, I obtain this condition. A is strictly less than C. So AC belongs to R5 composite R3 if A is less than C, that is first component is strictly less than second component, and that condition is the condition of relation R3. Therefore we can say that R5 composite R3 is nothing but R3. From this we can first write that R5 composite R3 is the set of all those ordered pairs AC in R2 such that A is less than C, and this is nothing but relation R3. So R5 composite R3 turns out to be R3. And last one is R6 composite R4. In R6 we have inequality, here less than or equal to. So let's find R6 composite R4 now. So here I am writing that part D, R6 composite R4. For R6 condition is inequality, ordered pair AB belongs to R2 if A and B are different, and in R4 condition is less than or equal to. AB belongs to R2 such that A is less than or equal to B. Again we consider arbitrary element in R6 composite R4. So this is true if there exists some real number B such that AB is in the first relation R6 and BC is in the second relation R4 for some real number B, for some B belongs to R. Now AB belongs to R6 implies we say that A is not equal to B. AB is in R6 if these two components are different or distinct, they are unequal. A and B are unequal, and BC is in R4. In R4 condition is less than or equal to. If first component is less than or equal to second component, then ordered pair AB is in R4. So here first component is B, second component is C. Therefore B is less than or equal to C. Now here we can see A and B are different and B is less than or equal to C. So what I can conclude from these two, A and B are different and B is less than or equal to C. So here we have to think that whether it is possible to find out existence of real number B such that these two conditions are satisfied. We can think on the real line also. Suppose I consider here I consider A and say C here, and suppose B is somewhere here. So is it possible for any ordered pair AC such that A is not equal to B and B is less than or equal to C? If I take any ordered pair AC, that means A and C are real numbers. Suppose A and C are any two real numbers, then whether it is possible to find out some real number b such that a and b are different and b is not equal to c. And we know that on the real line between any two real numbers there are infinite number of real numbers. So we can always find out at least one real number b between a and c such that a and b are different and b is less than or equal to c. If I take b equal to c, then I will have this condition satisfied. If I consider b is different from c, then I will have b less than c, and if I take b equal to c, then I have equality. So for any two real numbers AC belongs to R, we can say that AC ordered pair AC is in R cross R. So if I take any ordered pair in R2 or in R cross R, I can always find out some real number b or at least one real number b such that this condition is satisfied. A is not equal to b and b is less than or equal to c. So there is no restriction on these two real numbers. A and c can be any real numbers. So what is meaning of this? If we take any ordered pair AC in R2, then this implies that ordered pair AC is in R6 composite R4 also. That means R2 is a subset of this relation R6 composite R4. Why R2 is a subset of R6 composite R4? Because if we take any ordered pair AC in R2, then there always exists at least one real number b which satisfies these two conditions. A is not equal to b and b less than or equal to c. And R6 composite R4 is the set of all those ordered pairs which satisfy this condition. Therefore, R2 is subset of R6 composite R4, and it is clear that R6 composite R4 is a subset of R2 because R4 and R6 are subset of R2. Therefore, their composition is also a subset of R2. So, what is meaning of this? R6 and R4 must be equal. That means composition of R6 and R4 is nothing but R2 or R cross R. So this turns out to be universal relation R6 composite R4 equal to R2. So in this way you can decide the composition of given relations using the definition of given relation. Whenever you have infinite number of elements in the given relations, then you have to find out condition on the elements of ordered pair such that if ordered pair satisfies that condition, or if elements of ordered pair satisfies that condition, then ordered pair AC is in your relation. So in this way we can decide the composition of binary relations. And this is all about this session. I hope you like it. Thanks for watching, and your suggestions or your doubts you can ask in comment section. Again, thank you.